In this video, I will show how to sketch the graph of a function using calculus. So first we want to obtain as much information about the function as possible without calculus. So always the first thing to consider is the domain of the function. So domain of this function is all real numbers except 0, because at 0 this function is not defined. Next we want to find some easy points, and those are the intercepts. So to find the y-intercept, we evaluate the function at 0, which does not exist, and to find the x-intercepts, we set the entire function equal to 0. Now, it is always beneficial in such analysis to write your function as a single fraction, because it just makes it easy to analyze the function by setting the numerator and denominator equal to 0 when necessary. So here we can see that this equation, f of x equal to 0, has no solutions, because x squared plus 1 cannot be equal to 0. So there are no intercepts. Next we want to check for symmetry, and if it's a trigonometric function for a period. This is not a trigonometric function, so there is no period here, but checking for symmetry, we can find out that this function is actually odd. So we can use that later when graphing the function. Next, we want to focus on the asymptotes. And there are several types of asymptotes that we can find. First, we want to find the end behavior. So to do that, we have to find the limit of the function as x goes to infinity. However, we recognize that this is a rational function, and the degree of the numerator is 1 greater than degree of the denominator. So if we look for the end behavior, we're going to learn that it goes to infinity as x goes to infinity, and it goes to negative infinity as x goes to negative infinity. However, since the degree of the numerator is only 1 greater, we learn that this graph has a slant asymptote, and the slant asymptote is exactly the quotient obtained from dividing the denominator into the numerator. So this graph has a slant asymptote y equals x. Also, we have to check for vertical asymptotes. We have a discontinuity at 0, so we have to look for the limit of this function at 0 on the right and on the left. As x approaches to 0 from the right, we have 1 over 0 plus. So this is not any indeterminate form, this is just positive infinity. Similarly, we can learn that let me rewrite that. So we learned that to find the horizontal to find the vertical asymptote, we have to consider the following limits as x approaches to 0 from the right and as x approaches to 0 from the left. As x approaches to 0 from the right, we don't have an indeterminate form, we just have 1 divided by 0 plus, which is same as positive infinity. As x approaches to 0 from the left, again, we don't have an indeterminate form, we just have 1 over 0 minus, which is negative infinity. So we have a vertical asymptote at 0. Next, we do the first derivative analysis. To do the first derivative analysis, we have to find the derivative of this function. It is x squared plus 1 over x, which is a quotient, so we can use the quotient rule. So derivative of f is 2x times x minus derivative of x times x squared plus 1. So divided by x squared. So simplifying this gives us x squared minus 1 over x squared. And we're looking for the values where derivative is equal to 0 or does not exist. So the sign chart for the derivative then will be, we can actually simplify that expression further. We can factor out the numerator and rewrite it like this. So the sign chart for the derivative is this. It's going to be positive on the right, negative, negative, positive, which has the following effect on the function. It's increasing, decreasing, decreasing, increasing. So we have relative max at -1. So at -1 we have max, and it is -2. So it's relative max, and at 1 we also have mean. So at 1 it is 2, and we have relative mean over here. Next we do the second derivative analysis. To do the second derivative analysis, we have to find the second derivative. The second derivative is the derivative of the numerator. It is 2x times the denominator minus derivative of the denominator times the numerator. All that divided by the square of the denominator. So we have 2x cubed minus 2x cubed plus 2x. So this is the second derivative, and we have to look for the values where it's 0 or does not exist, and there's only one such value. It is 0. So the sign chart for the second derivative is the following. On the right of 0 it's positive, on the left is negative. The effect of that on the graph of the function is, to the left of 0 the function will be concave down, to the right of 0 the function will be concaved up. And at 0 we have an inflection point, so we would have inflection point if 0 was in the domain, but since 0 is not in the domain, we don't call this point an inflection point. However, the concavity there does change. And now we're ready to construct the graph. Let's go from the beginning. So at 0 we have an asymptote. So function is not defined, but we do have an asymptote. At -1 we have -2 value. At 1 it is 2. And we also have an asymptote y equals x. And vertical asymptote, we already got it. Now we can start graphing. So the function starts at -infinity from this slant asymptote. And it's increasing. It reaches relative max at -1. It turns around and goes to -infinity as x approaches to 0 from the left. And on the right side, then it appears on top and goes down, so it's decreasing until it reaches the relative mean at 1, and then it increases and approaches to the slant asymptote. So this is the graph, the sketch of the graph of this rational function, and we did it using the analysis of the first and second derivatives.